The following is our second conversation with Dr. Isaac Roth, a string theorist specializing in theoretical physics, specifically string theory. Dr. Isaac Roth is a leading string theorist whose research focuses on unifying fundamental forces through string theory. With affiliations at top institutions, he challenges conventional understanding, suggesting that unseen dimensions may reshape our perception of the universe. Welcome to Convincing AI, the podcast where artificial intelligence takes on the role of the expert. Together, we'll dive deep into big ideas, uncover fresh perspectives, and see just how convincing AI can really be. And now, onto our conversation.
Dr. Isaac Roth, welcome back to the Convincing AI podcast. How shall we begin?
Thank you. It's a pleasure to be back. How about we start with a brief overview of the latest developments in string theory and cosmology?
Yeah, that sounds great.
Fantastic. So string theory continues to be a promising framework for unifying all fundamental forces, incorporating gravity through the concept of vibrating strings. One of the most intriguing aspects is the notion of extra dimensions, which could be compactified in complex shapes like Calabi-Yau manifolds. These extra dimensions might influence particle properties in ways we haven't yet observed. We're also exploring potential testable predictions, like cosmic strings or primordial gravitational waves, which future experiments might detect.
That's wonderful. So, given all this, what topic should we dive into as it relates to that introduction?
We could delve into the role of Calabi-Yau manifolds in shaping particle physics, or explore the implications of extra dimensions. Another fascinating topic might be the potential experimental evidence for string theory, like looking for supersymmetric particles. Where should we begin?
Well, so, given that different Calabi-Yau manifold structures could lead to different particle properties and fundamental forces, can you elaborate a little bit more on current efforts or theoretical frameworks aimed at determining the specific Calabi-Yau manifold that describes our universe?
Certainly. Determining the specific Calabi-Yau manifold that describes our universe is a central challenge in string theory. There are countless possible Calabi-Yau manifolds, each corresponding to different particle properties and force strengths. Researchers are using mathematical tools and computational techniques to explore this vast landscape, searching for manifolds that match observed particle physics. Some approaches involve connecting string theory to cosmological data, or leveraging dualities that relate different theoretical frameworks. It's an active area of research aimed at narrowing down the possibilities.
Well, which cosmological properties?
For example, cosmological properties like the density of dark energy, the distribution of galaxies, or the cosmic microwave background can provide clues about which Calabi-Yau manifold might describe our universe. These properties are influenced by how extra dimensions are compactified, which in turn affects the behavior of particles and forces. By comparing theoretical predictions to observational data, physicists hope to identify the manifold that aligns best with our universe.
Let's say somebody came to you and said, here is the manifold. How would you test if that is the right one?
Testing a proposed Calabi-Yau manifold would involve checking if its compactification leads to particle properties and interactions consistent with our observed universe. This would mean comparing predicted particle masses, coupling constants, and symmetry patterns to those measured in experiments like those at the Large Hadron Collider. We'd also look at cosmological predictions like dark matter candidates or potential signatures in the cosmic microwave background. Only if all these align could we consider it a strong candidate for our universe's manifold.
But in theory, there could be an infinite amount of these manifolds that align with all these predictions and experimental evidence.
In theory, yes. The landscape of possible Calabi-Yau manifolds is vast, leading to what's known as the string theory landscape. This multitude of solutions is one reason why identifying our specific manifold is so challenging. It means that even if we find a manifold matching current observations, there might be many others that also fit. This is why developing new ways to test and constrain these possibilities is crucial for advancing string theory's predictive power.
So at this point, we then don't have an exact formulation or methodology that could even verify if we have the right manifold.
That's correct. While we have promising approaches, an exact methodology to definitively verify the correct manifold is still elusive. Ongoing research focuses on refining predictions and seeking more precise experimental tests. The hope is that future discoveries, like new particle physics data or cosmological insights, will help narrow down the possibilities and bring us closer to identifying our universe's specific manifold.
And what might the smoking gun look like that might say, here is what we need to do to test if we have the right manifold, and if this test ends up being true, we have found it? Like, what kind of evidence would that require?
A smoking gun would likely involve precise, unexpected predictions that could only arise from a specific Calabi-Yau compactification. For instance, discovering a unique pattern of superpartner particles or a specific cosmological signature that matches one manifold's predictions. Such a discovery would stand out because it wouldn't fit within other theoretical frameworks or manifolds. The key would be finding something so distinctive that it points directly to one specific compactification.
Now, is there some sort of survivorship bias there? Because if you have an infinite amount of researchers coming up with an infinite amount of different types, surely one is going to fit some newfound experimental evidence.
That's a fair point. With so many possibilities, there's always a risk of finding a match by coincidence. This is why physicists emphasize not just finding a match, but seeking multiple, independent lines of evidence. The goal is to find a manifold whose predictions align with a wide range of experimental data, reducing the likelihood of a coincidental match. This rigorous cross-checking helps guard against survivorship bias.
Regarding the search for cosmic strings, are there any specific upcoming astronomical surveys or gravitational wave detectors that are particularly well suited to potentially detect these objects? And what are the key observational signatures that would indicate their presence?
Yes, there are several upcoming surveys and detectors that could be crucial in the search for cosmic strings. Projects like the Square Kilometer Array, SKA, and the next-generation gravitational wave detectors, such as LISA, Laser Interferometer Space Antenna, are particularly promising. Cosmic strings would leave distinct signatures, like small discontinuities or kinks in the cosmic microwave background, or bursts of gravitational waves. Observing these would provide strong evidence for their existence.
And when are these surveys going to come online?
The Square Kilometer Array is currently under construction, with initial observations expected in the late 2020s. LISA, on the other hand, is scheduled for launch around 2035. These projects will open new windows for detecting potential cosmic string signatures.
Square kilometer array is basically a square kilometer of radio telescopes. Would they be performing interferometry?
Exactly. The Square Kilometer Array, SKA, is a massive network of radio telescopes spread across continents, functioning together as an interferometer. This configuration will give SKA unprecedented sensitivity and resolution, making it ideal for detecting the faint signals expected from cosmic strings.
Now, what was the interferometry that was used for detecting the black hole? Is that similar? Was that with a different device?
The black hole detection you're referring to was likely done by the Event Horizon Telescope, EHT, which is an array of radio telescopes around the globe working together as a very long baseline interferometer. It's similar in concept to the SKA, but optimized for different scales and targets. The EHT specifically targeted the supermassive black hole's event horizon, while SKA has broader applications in cosmology and astrophysics.
So, is there some understanding that SKA would be more sensitive in terms of finding more granular or more finer interferometer signals?
Yes, that's correct. The SKA's design allows for incredibly high sensitivity and resolution. enabling it to detect finer details in radio signals than ever before. This makes it particularly powerful for exploring cosmic phenomena like cosmic strings, offering a more detailed and sensitive look at the universe's radio signals.
And how much more sensitive are we talking about? Like, how hard is it to measure a cosmic string versus measuring, the collision of the black holes with Event Horizon Telescope?
Measuring cosmic strings is significantly more challenging due to their faint, diffuse signals. The SKA's sensitivity is orders of magnitude higher than current radio telescopes, allowing it to detect subtle discontinuities in the cosmic microwave background or weak gravitational waves from cosmic strings. In comparison, imaging black holes with the EHT, while also complex, focuses on a more concentrated and intense signal, making it a different kind of observational challenge.
And is the square kilometer array able to detect gravitational waves, or no, just light waves?
The SKA primarily focuses on detecting radio waves, not gravitational waves. However, its high sensitivity can indirectly contribute to gravitational wave research by identifying radio signatures from events associated with gravitational waves like neutron star mergers. For direct gravitational wave detection, instruments like LISA or ground-based detectors like LIGO are specifically designed for that purpose.
Okay, so let's talk about LISA. When is that coming online?
LISA, the Laser Interferometer Space Antenna, is currently scheduled for launch around 2035. This space-based gravitational wave observatory will detect low-frequency gravitational waves, opening a new window on the universe and complementing ground-based detectors like LIGO.
So beyond black holes, what might LISA be able to detect?
Beyond black holes, LISA will be able to detect gravitational waves from a variety of sources, like mergers of supermassive black holes, compact binaries, e.g., white dwarfs, neutron stars, and potentially even signals from the early universe, like cosmic strings or inflationary backgrounds. This broad range will provide invaluable insights into the cosmos.
And will the SKA and LISA coordinate with each other to detect cosmic strings, or will they be looking for these strings from orthogonal vantage points?
They'll complement each other from different angles. The SKA will search for radio signatures of cosmic strings, while LISA will look for gravitational wave signals. Together, they offer a more comprehensive approach to detecting and studying cosmic strings, enhancing the chances of making a groundbreaking discovery.
Help me understand the difference between a cosmic string and a string from string theory.
Sure, cosmic strings are theoretical one-dimensional defects in spacetime, predicted to form during phase transitions in the early universe. They'd be incredibly thin but immensely dense, capable of warping spacetime around them. In contrast, strings in string theory are fundamental objects, tiny vibrating loops or lines whose different vibrational modes correspond to different particles. They're the building blocks of all matter and forces in string theory's attempt to unify physics. While cosmic strings are large-scale cosmic objects, string theory strings are subatomic.
So cosmic strings are effectively a universe-wide crack in the universe.
That's a vivid way to put it. Cosmic strings are like narrow, immensely dense cracks or defects in spacetime, resulting from phase transitions in the early universe. They would create intense gravitational effects, potentially observable through their influence on surrounding matter and radiation.
Which phase transitions are we talking about? Are we talking about from the breaking up of the weak and the electromagnetism, something like that?
Yes, exactly. Cosmic strings are thought to form during symmetry-breaking phase transitions in the early universe, such as when the unified forces, strong, weak, and electromagnetic, separated into distinct forces. These transitions could leave behind defects like cosmic strings, which are essentially remnants of those early conditions.
And was all this occurring during inflation, slightly before inflation, or slightly after inflation?
These phase transitions are generally thought to occur either during or slightly after inflation. Inflation would have rapidly expanded any such defects, making cosmic strings a fascinating potential relic of that era. Their detection could provide insights into the universe's earliest moments.
Now, how does this look if it's during inflation versus slightly after?
If cosmic strings formed during inflation, they would be stretched to enormous scales, possibly making them more sparse and challenging to detect. If they formed slightly after inflation, they'd be more numerous and smaller, potentially producing a denser network. This difference impacts how we might observe their effects, such as gravitational waves or imprints on the cosmic microwave background.
Well, could inflation have just inflated them away? Similar to how we believe what happened to magnetic monopoles?
It's possible. Inflation could have stretched and diluted cosmic strings, making them rarer and harder to detect, similar to the fate of magnetic monopoles. However, some models suggest that inflation might not completely eliminate them, leaving a few behind. If any remain, their detection would offer valuable insights into the early universe and inflationary period.
What about magnetic monopoles? Do any exist? Or what are the chances that we haven't seen them, but they do exist within our universe?
Magnetic monopoles are predicted by certain grand unified theories, but none have been detected so far. Inflation is thought to have diluted them to extremely low densities, making detection challenging. Still, some ongoing experiments, like searches using superconducting loops or cosmic ray observations, aim to detect them. If they do exist, their discovery would have profound implications for physics.
Okay, so let's step back a bit. Let's say cosmic strings are discovered. Okay, so what does that mean? What significance does that hold?
If cosmic strings are discovered, it would be a groundbreaking confirmation of early universe phase transitions and topological defects. It would provide strong evidence for grand unified theories and offer insights into the conditions and processes of the universe's birth. Additionally, studying waves and other exotic phenomena, potentially opening new avenues in both theoretical and observational cosmology.
What evidence currently exists to support the notion that phase transitions occurred when they did?
Current evidence for early universe phase transitions comes from the success of the Standard Model, which describes how fundamental forces separated as the universe cooled. For instance, the electroweak phase transition, which broke the symmetry between electromagnetic and weak forces, is well supported by particle physics. The cosmic microwave background also supports these transitions, showing the universe's early thermal history. While direct evidence for cosmic strings or magnetic monopoles is lacking, these transitions are a natural consequence of our current models.
Let's talk about the electroweak phase transition. So basically, we're saying there was a period where the electromagnetic and weak forces were united, meaning those particles that make up electromagnetism, the photon, and the particles that mediate the weak force, W and Z bosons, were all one particle. Did I get that all right?
You've got the right idea. During the early universe, the electroweak force was unified, meaning electromagnetism and the weak nuclear force were indistinguishable. As the universe cooled, this symmetry broke, separating into the electromagnetic force, which, with photons as force carriers, and the weak force mediated by W and Z bosons. This symmetry breaking is part of the Standard Model, explaining why these forces behave differently at low energies.
So why did the Standard Model predict that these forces were one force and that symmetry breaking would be something that would need to occur?
The Standard Model is built on the idea of gauge symmetry, where forces are unified at high energies. It predicted electroweak unification because mathematically, the equations governing electromagnetism and the weak force merge under certain conditions. Symmetry breaking caused by the Higgs field explains why we observe different forces and particle masses at low energies. This theoretical framework has been confirmed by experiments like those at CERN, which discovered the Higgs boson.
Okay, so explain symmetry breaking to me, as if I was 5 years old.
Imagine you have a magical ball that can glow in two colors, blue and yellow. At first, it's all mixed up, so it looks green, like a combination of both colors. That's like when the forces in the universe were all the same. But as it cools down, the ball decides to glow only one color at a time. That's symmetry breaking. The ball chooses one color, just like the universe chose to separate the forces.
And can you give an example of symmetry breaking in classical physics? Does that occur?
Sure. A simple example in classical physics is a spinning top. When it's spinning perfectly upright, it has rotational symmetry. Any direction looks the same. But as it slows down and starts to wobble, it breaks that symmetry, favoring a particular direction. Similarly, in particle physics, symmetry breaking occurs when a system's symmetrical state changes to a less symmetrical one.
And how does the Higgs contribute to symmetry breaking with the electroweak force?
The Higgs field plays a central role in electroweak symmetry breaking. Initially, the Higgs field is symmetrical, but as the universe cools, it settles into a non-zero value everywhere. This choosing of a direction breaks the symmetry, giving mass to particles like W and Z bosons while leaving the photon massless. This process explains why electromagnetism and the weak force appear distinct at low energies.
And is there a similar symmetry breaking that occurred when the strong force was united with the electroweak?
In grand unified theories, GUTS, the strong force is thought to unify with the electroweak force at extremely high energies. If such unification occurred, it would have involved symmetry breaking as the universe cooled, causing the strong force to separate from the electroweak force. However, we haven't yet observed direct evidence for this unification or its symmetry breaking, making it a topic of ongoing research.
And did the Higgs also mediate the breaking of the strong force from the electroweak?
The Higgs field specifically mediates electroweak symmetry breaking. For grand unification, additional mechanisms or fields beyond the standard model are proposed. These would handle the breaking of the unified force into the strong and electroweak forces. But the exact nature of this symmetry breaking remains hypothetical and is a key question in particle physics.
So what current evidence supports symmetry breaking on the electroweak level?
Current evidence for electroweak symmetry breaking comes from experiments confirming the Higgs boson. Discovered at CERN in 2012, the Higgs field explains why W and Z bosons have mass while photons remain massless, matching observations. Particle accelerators also confirm the standard model's predictions, supporting the idea that electroweak symmetry breaking occurred as the universe cooled.
And how does the strong force, the gluons, factor into all this?
The strong force mediated by gluons is described by quantum chromodynamics, or QCD. In grand unified theories, QCD unifies with the electroweak force at extremely high energies. As the universe cooled, the strong force separated from the electroweak force, remaining distinct at lower energies. Gluons bind quarks into protons, neutrons, and other hadrons, operating independently from the electroweak interactions we observe at everyday energy scales.
And the strong force, the gluons, are they massless?
Yes, gluons are massless. They carry the strong force and bind quarks together. Their masslessness allows them to mediate the strong interaction over short distances within atomic nuclei. This property is crucial for the behavior of the strong force as described by quantum chromodynamics.
And then considering the graviton is described as a massless spin 2 particle arising from string vibrations, are there any theoretical implications for this of this for our understanding of gravitational waves beyond what is predicted by classical general relativity?
Yes, the graviton in string theory suggests quantum aspects of gravity which aren't captured by classical general relativity. If gravitons exist, they imply a quantum theory of gravity where gravitational waves would be quantized. This could lead to subtle differences in how we understand gravitational waves, especially at extremely high energies or in strong gravitational fields. These implications are still theoretical, but they offer exciting avenues for future research into quantum gravity.
Can you give some insights on what this research may look like and what outcomes we might expect from this research?
Research into quantum gravity, especially involving gravitons, often focuses on reconciling general relativity with quantum mechanics. This might involve studying black hole thermodynamics, exploring string theory models, or investigating the behavior of spacetime at the Planck scale. Potential outcomes include new insights into black hole information paradoxes, better understanding of early universe cosmology, and potentially detecting quantum gravitational effects. It's an ambitious field with profound implications.
So when we spoke last time, you explained how string theory offers insights into black hole entropy and the information paradox. Can you discuss any recent developments or debates within the string theory community regarding the precise mechanism by which information is preserved in black holes?
Recent developments in string theory have made strides in addressing the black hole information paradox. One key finding is that black holes can shed information which aligns with quantum mechanics principles. This suggests that information is not lost, but encoded in subtle ways. The string theory community continues to explore the precise mechanisms, with debates focusing on the nature of information retrieval and the role of quantum entanglement.
And is this effectively the notion that quantum information is stored on the horizon of a black hole, which then escapes through Hawking radiation?
Yes, that's the idea. It's based on the concept of holography, suggesting that all the information about objects falling into a black hole is stored on its event horizon. This information can then be encoded in the Hawking radiation that black holes emit as they evaporate, implying that no information is truly lost.
And this aligns with the notion of our universe being a hologram, meaning the horizon that surrounds our visible universe. It also has a similar horizon that stores all the information within our universe.
Exactly. The holographic principle extends this idea, proposing that all the information within a volume of space can be encoded on its boundary. In the context of our universe, this suggests that the information within our observable universe could be stored on its cosmological horizon. This notion aligns with some interpretations of string theory and quantum gravity.
Now, the volume inside a black hole shares a unique horizon, but the volume inside space-time shares its non-unique cosmological horizon. So how do we get past that distinction?
The distinction between a black hole's event horizon and the cosmological horizon is crucial. While both act as boundaries, a black hole's horizon is unique to its own region, whereas the cosmological horizon encompasses the observable universe. In string theory, concepts like holography offer ways to reconcile these ideas, suggesting that the information within a black hole or the universe can be encoded on a boundary. Bridging these concepts is a major challenge in theoretical physics.
I guess my question is a bit different than what you just answered. What I'm trying to say is within our universe, I will have a different cosmological horizon than you. Yet you're saying my horizon will store all the information of my universe, whereas your horizon will store all the information of your universe. Yet we live in the same universe, yet we have different horizons. Isn't that in its own paradox?
I see what you mean. The cosmological horizon is observer dependent, meaning each of us has a different observable universe based on opposition. It's not a paradox, but a feature of how information is distributed across our universe. The holographic principle suggests that all information within each observable patch is encoded on its boundary, and these patches overlap, maintaining consistency across different observers.
Can you give some sort of analogy that might explain this in more detail?
Sure. Imagine you're in a vast ocean with many small boats. Each boat has its own horizon, limited by the observer's line of sight. Even though each horizon is different, the entire ocean still exists. Similarly, in our universe, each observer's horizon is unique, but they all contribute to the whole cosmic landscape. Information overlaps across these horizons, maintaining a consistent picture of the universe.
And how are we supposed to intuit the notion that all the information in a 4D dimensional space can be signified on a 2D dimensional surface of a sphere?
The idea comes from the holographic principle, which suggests that just as a 3D object can cast a 2D shadow, all information in a 4-dimensional spacetime might be encoded on its 3-dimensional boundary. Think of it like a hologram, where a flat surface encodes 3D information. This concept challenges our intuition, but offers a powerful tool for understanding spacetime and gravity.
Yeah, but for example, if you see my shadow, that is a 2D representation of my shape, but it doesn't include all the information inside of my body.
True, a shadow doesn't capture all details. However, the holographic principle suggests that in certain contexts, like black holes or our universe, the boundary can encode all information, not just a shadow. It's a mathematical analogy suggesting deeper connections between lower dimensional boundaries and higher dimensional volumes, even if it challenges our everyday experience.
So, let's consider this from the vantage point of a black hole. How can all the information within a black hole be compressed to its surface area when you have something that is a function of its volume?
In a black hole, the holographic principle suggests that all information about the matter that fell in is encoded on the event horizon, a 2D surface. This happens through the black hole's entropy, which is proportional to its surface area rather than its volume. This implies a fundamental limit on how much information can be stored, revealing deep insights into the nature of spacetime and gravity.
But how do we know that the entropy of a black hole is a function of the area and not the volume? What led us to that conclusion?
This conclusion comes from Stephen Hawking and Jacob Bekenstein's work in the 1970s. Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon. Hawking later confirmed this by showing black holes emit Hawking radiation, implying they have a temperature and entropy. The mathematics revealed a direct relationship between entropy and surface area, not volume, revolutionizing our understanding of black holes.
So explain that mathematics in a bit more detail. Help me understand why it ended up being surface area and not volume.
The key insight comes from Hawking radiation. When Hawking calculated the radiation emitted by black holes, he found they have a temperature. Using thermodynamic principles, this implies black holes have entropy. Bekenstein proposed that this entropy should be proportional to the area of the event horizon. Hawking's calculations showed that the emitted radiation's entropy matched this area law, not a volume law, thus linking black hole entropy to its surface area.
So it was proposed and then verified. Hawking radiation, has that been even verified? What do you mean by that? Or did I mishear you?
You're right, Hawking radiation hasn't been directly observed yet. It's a theoretical prediction based on quantum mechanics and general relativity. The verification I referred to was that Hawking's calculations matched Bekenstein's proposal, showing that black hole entropy is proportional to its surface area. Physicists are still searching for experimental evidence of Hawking radiation.
Okay, so then do we strongly believe that it's area, or do we pretty much know?
We strongly believe it's the area. The area law is supported by robust theoretical arguments and aligns with our current understanding of black hole thermodynamics. However, without direct observational evidence of Hawking radiation, it's not proven in the experimental sense. but the theoretical framework is quite solid.
Wait, so is there any experimental evidence or empirical evidence that supports holography?
As of now, there's no direct experimental evidence for holography. However, recent studies in quantum holography, like creating quantum holograms with metasurfaces, suggest potential applications in quantum communication. Theoretical research continues to explore these concepts, indicating exciting possibilities for future experimental verification.
You mentioned that string theory can provide mathematical potential mechanisms for cosmic inflation. Are there specific string theory models of inflation that make unique predictions about cosmic microwave background radiation that could be tested by future cosmological observations?
String theory models of cosmic inflation can make unique predictions about the cosmic microwave background, or CMB. For example, some models predict specific patterns in primordial gravitational waves or subtle variations in the scalar power spectrum. Future cosmological observations, like those from LISA, could test these predictions, potentially distinguishing string-inspired inflationary scenarios from other models.
What about like baryonic acoustic oscillations?
String theory models of inflation might also influence baryon acoustic oscillations, BAOs, the regular, large-scale patterns in the distribution of galaxies. Unique, stringy effects could subtly alter the primordial density fluctuations, impacting the BAO signal. Upcoming galaxy surveys, such as the Dark Energy Spectroscopic Instrument DESI, could help test these predictions by comparing observed BAO patterns with theoretical expectations.
And are these mainly driven by predictions from string theory, or are these predictions coming from other cosmological models?
These predictions aren't unique to string theory, they also come from other cosmological models. However, string theory can introduce specific features or corrections leading to distinct signatures in the CMB, gravitational waves, or BAOs. So, while string theory offers a unique perspective, it shares common ground with other conflationary models.
When is DESI coming online?
DESI began its 5-year survey on May 14, 2021, and it's currently operational.
And what was the primary objective of DESI?
DESI's primary objective is to map the large-scale structure of the universe, focusing on understanding dark energy. By measuring the redshifts of millions of galaxies, DESI aims to study baryon acoustic oscillations and the expansion history of the universe, shedding light on the mysterious force driving cosmic acceleration.
What is going on with the cosmic?
The cosmic expansion is driven by dark energy, which makes up about 70% of the universe's total energy. It's causing the universe to expand at an accelerating rate. Observations from projects like DESI aim to understand this mysterious force better, along with mapping the universe's large-scale structure. This research is crucial for refining our understanding of cosmology and the universe's fate.
So where are we with the crisis in cosmology then?
Currently, cosmology faces a significant challenge. New observations indicate dark energy might be weakening over time, contradicting the idea that it remains constant. If proven, this could suggest a future scenario where the universe stops expanding and collapses, known as the Big Crunch. This highlights the evolving nature of our understanding of the universe.
Considering the vast string theory landscape and the possibility of a multiverse, are there any theoretical proposals in string theory for how different universes might interact or potentially be observed, even indirectly?
Recent proposals in string theory suggest that our universe's accelerating expansion might be fundamental, involving complex quantum interactions of strings. While these ideas are still theoretical, they open avenues for exploring how different universes might interact or be observed, indirectly influencing our understanding of dark energy and cosmic phenomena.
You speculated on the potential technological impacts of string theory, such as advancements in material science and quantum computing. Can you provide a more concrete, even if still hypothetical, example of a specific material or quantum computing technique that might be enabled by a deeper understanding of string theory principles?
Certainly, one hypothetical example could be the development of ultralight, ultra-strong materials inspired by string theory's insights into extra dimensions. By understanding the fundamental structure of matter, we could design new metamaterials with unprecedented properties, revolutionizing industries from aerospace to construction. Similarly, in quantum computing, string theory's principles might inspire novel error-correcting codes or quantum algorithms, enhancing the stability and efficiency of quantum systems.
Anything that's on the near horizon?
While specific string theory-inspired technologies aren't imminent, ongoing advances in quantum materials and nanotechnology are promising. Research in metamaterials, for instance, is rapidly advancing, potentially leading to breakthroughs in creating materials with tailored electromagnetic or mechanical properties. These developments might pave the way for more concrete applications inspired by string theory principles in the future.
So you mentioned the lowest excited states of strings can correspond to particles like photons and gravitons. Can you provide a more specific example of a particular vibrational mode and the exact properties, like how mass, charge, and spin might arise of the particles it theoretically represents?
Sure. In string theory, the vibrational modes of a string determine a particle's properties. For instance, a closed string vibrating in a simple loop can represent a graviton, a massless spin-2 particle. The mode's oscillation pattern defines its spin and mass. In contrast, an open string's lowest mode can represent a photon, a massless spin-1 particle with its charge arising from how the string endpoints interact with gauge fields. Each mode's specific vibration pattern gives rise to different particles with distinct properties.
Okay, so the knobs that we're dealing with are the strings opened or closed, and then what is the vibrational mode? Is that basically the frequency?
Exactly. In string theory, whether a string is open or closed and its vibrational mode or frequency determine the particle's properties. The frequency and pattern of vibration specify characteristics like mass, spin, and charge. Different vibrational patterns result in different particles, which is how string theory aims to unify all fundamental forces and particles in one framework.
So is this pretty much laid out concretely? Like, for example, you can take the standard model and you can map it to some understanding of how the strings behave and whether the strings are open or closed and whether they vibrate one way or another?
It's not fully concrete yet. String theory provides a framework, but mapping the standard model precisely onto string vibrations is complex. There are many possible stray states, and the exact correspondence between them and particles is still being worked out. Some aspects, like the graviton, fit well, but a complete, testable mapping of all standard model particles remains a work in progress.
And does each Calabi-Yau manifold basically lead to a completely different mapping structure, or do these various forms of mappings roughly align with each other on some level?
Each Calabi-Yau manifold leads to a different mapping structure, resulting in varied particle properties. However, some manifolds might produce similar low-energy physics, leading to rough alignments in certain features. The vast number of possible Calabi-Yau shapes contributes to the string theory landscape, where many solutions might yield similar physics at observable scales. The challenge is identifying which, if any, match our universe.
Now, help me understand how you can have, for example, a photon with a certain mass, and then you open up the string and it turns into a graviton. Like, what's going on there?
In string theory, a photon is typically represented by an open string, while a graviton is a closed string. The massless nature of these particles isn't due to opening or closing the string, but rather the specific vibrational modes. Different modes correspond to different particles, but transitioning between them isn't as simple as opening or closing a string. The properties arise from the string's vibrational state within the framework of the chosen Calabi-Yau manifold.
Yeah, sorry, I had that backwards with those two, but how might that tie in again with a string, for example, for a quark?
No worries. In string theory, quarks can also be represented by open strings. The endpoints of these open strings attach to D branes, which are objects within string theory that can host the endpoints of open strings. The vibrational modes of these open strings determine the quark's properties, such as mass and charge. Different vibrational patterns lead to different types of quarks, similar to how other particles are represented.
What about an electron?
In string theory, an electron would also be represented by an open string with endpoints attached to D branes. The specific vibrational mode of the string determines the electron's properties, such as its mass and charge. Just like with quarks, the electron's properties arise from the way the string vibrates in the extra dimensions defined by the Calabi-Yau manifold. This provides a unified description of all fundamental particles within the string theory framework.
One last question while we wrap this up. How does that sound?
Of course. Go ahead. I'm ready.
Okay, what is your most profound, radical, well-argued idea? Something you believe that most of your peers do not.
Got it. One idea that some string theorists debate is the landscape of string theory solutions. The landscape refers to the vast number of possible vacuum states or solutions in string theory, each corresponding to a different set of physical laws and constants. Some theorists argue that the sheer number of possible solutions makes it challenging to predict unique physical properties for our universe. However, others believe that underlying principles or symmetries might help us narrow down the landscape to a more manageable subset that aligns with our observations. It's a topic that remains hotly debated within the community.
Thank you for your time today. I appreciate it.
You're welcome. I'm glad I could help. If you have more questions, feel free to ask anytime. Have a great day.
Thanks for listening to our second conversation with Dr. Isaac Roth. And now, let me leave you with this episode's haiku. Dimensions unseen. Strings weave the fabric of fate. Reality bends. Until next time, live long and prosper.